Hi, welcome to the SunRISE Ground Radio Lab. I am Dr. Samantha Blair, and I'm a physics and astronomy professor at Dalton State College, as well as a member of the Radio Joke team. Here are the contributors to the program, as well as acknowledgments of the funding agents who make this program possible. And this training module will be about galactic radio emissions. This is training module 1.5. Prerequisites for this training module and all of the other ones are some basic math and understanding of general science, understanding the electromagnetic spectrum and how items like speed, wavelength, frequency, and energy are related, being able to understand a graph, and then hopefully you've gone through training module 1.4 and in that understand the mechanism behind the emission of this radiation. But in this module, we will learn how these galactic radio emissions were first noticed, how the galaxy is positioned in relation to Earth and to Earth's celestial equator, how the 20.5 megahertz radio waves are generated by the galaxy, and then what the galactic hump represents. So as far as how these radio emissions were first discovered, Carl Jansky is the one who discovered them in the 1930s, and he was a radio engineer working at Bell Labs, and he was looking for radio frequency interference in overseas radio communications, and he was using this telescope that you see in this image here, dipoles. It's on a circular track that rotates. It was actually termed the merry-go-round. Okay, and he noticed a source that rose 4 minutes earlier each day. The frequency was 20.5 megahertz, and this source passed overhead twice a day. And the peak of this radiation was towards the constellation Sagittarius, which we know is the galactic center. Okay, and from this discovery, ultimately the field of radio astronomy was born. Our galaxy itself is a thin disk of stars, gas, and dust, all right? But everything is not just sitting in a plane, okay? So it's not like we have the sun and the earth going around it, and that's all just in a flat plane, oriented flat with respect to the galaxy in the galactic center, all right? As you see here, the celestial equator is the area that's in blue, that blue plane, and that's a extension of the Earth's equator out into space. The ecliptic plane is the path the sun takes through the sky. That's assuming we feel like we're going straight up and down. We know we're actually tilted as we go around the sun, all right, at a 23.5 degree angle. But if we feel like we're straight up and down, it makes the sun look like it moves at an angle through our skies at a 23.5 degree angle. So that ecliptic plane and that celestial equator, all right, meet twice a year. And when the sun is sitting at either of those positions, it's either the first day of spring, the vernal equinox, which is this point at the front, or it's the first day of fall, which would be the point behind. And when it's at its highest point, it's summer solstice, and its lowest point, 23.5 degrees below the celestial equator, it's winter solstice, all right? But as you see here, this galactic plane, all right, is cutting through all of this, all right? So this is the galactic equator. This is the center of the galaxy, and as you can see, the North Galactic Pole is just shooting through the center of this, and this North Celestial Pole, which is an extension of the Earth's North Pole into space, is going to be at a 63-degree angle to one another. So, because of this inclination, the galaxy passes overhead once every 12 hours, all right? And so every other transit is pointed towards the galactic center, and that's where the radiation is going to be most intense. Why do we receive this background radiation from the galaxy? Well, believe it or not, our galaxy actually has weak magnetic fields associated with it. These magnetic fields are less strong than the Earth's magnetic field that's generated in the liquid portion of our core, all right? And when charged particles are accelerated to relativistic speeds along magnetic field lines, accelerating charged particles give off radiation. And in this case, the synchrotron radiation is at radio frequencies, all right? Frequencies frequently less than 30 megahertz, okay? And so that's what we pick up. And so this diagram shows you there's a magnetic field line here, and then this electron has a component of the velocity that allows it to spiral in a direction, all right? And that's what we're seeing, directional spiraling here of this electron. And as it's doing that, we see this synchrotron radiation being given off, which for our intents and purposes is, he picked it up at 20.5 megahertz, all right? Now, Jansky made the first discovery, but Grote-Reber kind of really started the field of radio astronomy because he took what Jansky did and said, okay, I'm actually going to look more deeply at the galaxy. On the right here, we see the first radio map of the Milky Way, all right, at 160 megahertz. Okay, and we can see the galactic center here. On the left, we're looking at a 1400 megahertz picture of the galaxy that was done later, all right, or more recently for us. And we see the galactic center, we see Cygnus, and we see Cas A, okay? And we see all three of these here. Here is positive 90 and negative 90 in declination, and we can see right ascension. So this is the same setup that we have from our celestial equator, and so it just shows how the galaxy looks from Earth. So the radio Jove receivers can detect the low frequency radiation that comes from the galaxy. Jansky detected it at 20.5 megahertz, and the radio Jove receivers now can detect anywhere from 16 to 24 megahertz. So it's definitely doable, and we always have been able to, even with the single frequency receivers that we used before. In a 24-hour period, you get the two distinct, what we call galactic humps, all right? And so at 0550 on this graph in time UTC, you can see this first small little hump. And then at 05, at 1550, you can see the second one, which is the larger one, the more distinct hump, all right? Now the galactic hump at 1550 represents the hump that's towards the galactic center, and that's why the radiation peak is stronger there in antenna temperature, which represents signal strength, essentially. Now, the radio Jove receivers also allow you to take spectrogram data, all right, where we're looking at frequency versus time. And as you look at this specific spectrogram, we're looking at 24 hours of data, okay? And at position number 1, we're looking at the gradual brightening and decay, showing the galactic plane passing overhead. Each of the different numbered regions represents something different. Spectrograms are very interesting. At region 2, you're looking at citizen or regular people's radio communications. At region 3, you're looking at some HF, radar emission. At region 4, you're looking at some amateur radio and shortwave broadcast signals. Region 5 is shortwave broadcast. Region 6 is a solar burst. And region 7 is probably, other than the galaxy passing overhead, the more interesting one. The triangular, they're TP-shaped, regions, all right, showing time-varying increase in band noise due to terrestrial ionospheric propagation effects, enabling natural emission from distant lightning to be received. So that's kind of neat. We're looking at lightning there. So as you can see, the spectrogram also shows the galaxy passing overhead. So that basically concludes the information for galactic radio emissions and how we detect them. If you want more information, there's some resources here broken up into Carl Jansky, the galactic hump, and galactic synchrotron radiation, if you're more interested in different types of material. If you're interested in Grote Reber, you can certainly look him up and see the kind of work that he did as well. Thank you for listening. Thank you for your attention, and good luck with all your observing. Clear skies.